So in this video I want to talk about the forces that are acting on architectural structures, and the particular structure that we're going to talk about is the post and lintel structure. So there are two main forces that act on the materials that are used to build architectural structures, and they are tension and compression. So let's start talking about compression first of all. So when you apply a force and you push in on a material from both ends, and it is being pushed, then we say that that material is in compression. It's being squashed is a good way to think about it. While as if you pull on a material, then we say that that material is in tension. So these are the two main forces. It's a push and a pull. So when you are pushing on a material, it's in compression, and when you're pulling on it, it's in tension. So if we look at this, we see a little diagram showing some different building materials. So this chart shows a number of different building materials. So let me start off by just looking at a couple. We have sandstone, limestone, brick, or marble and brick. All of these you can think of as stone. What I want you to notice is that they are very strong, all of them, in compression. So if you put a lot of compressive force on these types of materials, they won't break. They're very strong in compression. But if you compare their tensile strength, you'll see that all of them are very weak in tension. So what that means is that stone is a great building material if you're using it in a situation in which it's undergoing compression. It's the perfect material for it in that sense. But you would never want to use stone when it is placed in a position where it's undergoing tension, because it will just break very, very easily. Now let's compare that with another common building material that's still used all over the world today, which is wood. Now if you look at its compressive strength, it's not as strong as stone, but it's still pretty strong. But what makes wood so useful is that its tensile strength is much, much stronger than stone. In actual fact, its tensile and compressive strength are about the same. So wood is a great material because it's relatively strong in both tension and compression. And then lastly, if we compare stone and wood to steel, which is a modern material, you can see that steel is very, very strong in compressive and very, very strong in tensile or in tension. So it really is one of the main building materials of choice today is steel, because of its incredibly high compressive and tensile strength. Now a thing to note here, we have another very common building material that's not represented in this chart, which is concrete or reinforced concrete. And so the way to think of concrete is like stone. It's very, very strong in compression but weak in tension. And as we're going to see, reinforced concrete, it actually contains steel in it. So really what it is it's a mixture of stone and steel. And that way it has both compressive and tensile strength. So let's now look at the post and lintel system and the forces that are acting upon this system. So first of all, what is a post and lintel system? Sometimes it's also referred to as a trabeated system. So let's start off by talking about the horizontal element in the system. So up here you can see these stone blocks which are horizontally aligned. We refer to these as the lintels, hence it's the lintel part of the post and lintel system. But sometimes they're referred to as beams or headers or architraves. The vertical component, which in this case is these columns, are referred to as the post, or sometimes the prop, or a column, or a pillar. And that is why, hence, the post and lintel system. This system of architectural design or architectural structure is very commonly used today in modern structures like apartments and houses, but typically they're built of steel today. But in the past they were very common in ancient Egyptian, Greek and Roman architecture, usually made of stone though. So let's now look at a Greek temple as an example. So you can see we have our columns here, actually make that a. And we have our lintel here. I want you to imagine that above here on the roof is a very heavy roof system with wooden beams and battens supporting very, very heavy terracotta tiles. And so the weight of that system is pushing down on the temple. It's putting a load on the temple. What happens to that load? Well, it is transferred down into the columns. So the columns take that load, that force, it travels down the columns, and at the same time the earth or the ground is pushing up, of course. And so what we have are the columns being in compression. And so it makes sense that you would make these columns out of stone because stone is very strong in compression. So what's going on in the beam? Well, the beam is a little bit more complicated. So let's sort of imagine we're going to take the beam out of this temple and just treat it as a separate unit or element and analyze it. So here's our beam. I want you to realize that in this example we're going to have two columns on either side that are supporting this beam. And then we're going to push a load down or put a load on the middle of the beam. So how will this beam act when you put a load on it? Well, it's going to bend. So here is our beam, it's bent. And I've sort of put these vertical lines on our beam just to sort of give you a sense of what actually is going. So if you look down here, you might notice what has happened to the beam. You should notice that there is a difference between the top of the beam and the bottom of the beam. And what's actually happened at the top part of the beam is it's being pushed together. It's undergoing compression. Whereas the bottom part of the beam, as it bends, is pulled apart. It's undergoing tension. So in beams, you have both tension and compression happening. The critical thing to note, though, is that the compression is happening in the top part of the beam, whereas the tension is happening in the bottom of the beam. And in the middle of the beam, believe it or not, there is neither tension or compression happening in the middle of the beam. So that raises a bit of a challenge when you're building temple out of stone. Ideally you want to use stone because it's a beautiful material, it's going to last a long time, it's expensive, and you're really building temples in these ancient Greek city-states to impress your neighbors. So it's a bit of an issue though, because as we have already talked about, stone is very strong in compression but weak in tension. And so we know that tension is going to be happening at the bottom of the beam. So one of the limitations on architectural structures and design in the ancient world was just how far apart you could put columns. Or another way of expressing that is the limit on the length of the lintel. And so about the widest gap you could have between a column is about 11 meters or 36 feet if you want to span that using stone. Because if you do anything bigger than that, you're going to have a problem. And this is what's going to happen. What's going to happen is it's going to crack. Remember, at the bottom of the beam is where tension is happening. And stone is extremely weak in tension. So it's going to crack there, and then the whole thing is just going to collapse. So this is a major limitation on the prop and lintel system, particularly if you're building out of stone, is how long or how wide you can have a lintel. There's actually a limitation on this. And so this meant there was a limit on just the inner dimensions that you could span with stone lintels in these ancient temples. Now if you did want to span a greater gap, then you had to use a material that was not stone. So the answer back in ancient Greece was to replace stone beams with very, very long wooden beams. But once again, there was a limit to that because of the size of the trees, and even if the beam is really long, it would also crack as well. Now today, of course, we deal with this by using steel, but of course the ancient Greeks and Romans didn't have steel to use. So hopefully that is a summary of the prop and lintel system and the forces that act in or on prop and lintel systems, and then the properties of some of the most basic building materials. So use this to help you when you want to make a video demonstrating how different structures will act under different forces.